Yeah! Welcome back to Fat Mama Physics. Today's video, we are going to talk about elevator problems featuring Captain Levi from Attack on Titans. I even got my Attack on Titan t-shirt. And get the mic out of the way. Here you go. Rawr. Okay. So let's get the show on the road. Get my mic back in place. So, elevator problems. Here's a few questions before we start off, and the questions we will be answering in this video. When you're in the elevator, why do you feel heavier or lighter? Oh, if you've never been in an elevator, maybe try to go on one today. How does your weight, does your weight change in an elevator? So basically, why is it that you feel heavier or lighter in this elevator? In order to do that, let's take Levi, put him on this elevator, and just show us what is happening with this elevator. And what I'm going to do is I'm going to play a little animation of him doing that, and what you're going to do is you are going to tell me when would he feel heavier, when would he feel lighter, and when would he feel no difference in his weight. This is a good time to actually, well, here, let me play the animation first. The animation's a little cranky there. Hopefully it's not too bad on your end. Okay, so this is a good time to pause the video for you to brainstorm these three things. Tell me those points in his motion that he would feel that, and we will come back, discuss it, and we will use this as the basis for the rest of the video. Okay? Good time to pause. Alright, so let's talk about the entire motion here. So here is him going up. Bam. Okay, so you might have noticed if you said at the very bottom as he was about to go up, he's going to feel heavier when the elevator is moving up. You are absolutely correct. And at the very top, in the middle of the elevator ride, where the elevator is just moving upwards, he doesn't feel any change in his weight. No change, okay? At the top of the ride, where the elevator is slowing down, that's where he would feel lighter. Yes, you are right. That's where he would feel lighter. On his way down, okay, at the very top, when he's about to come down, he would feel lighter at the very top, okay? And then in the middle, he would again feel no change. And then at the very bottom, when the elevator is slowing down, coming back to the bottom floor, he feels heavier, okay? So absolutely, if you got these, you are absolutely correct. And of course, the last time when he would feel no difference in his weight is when the elevator is at rest, okay? So here are the solutions. This is what we talked about. I just categorize them in each of these segments. So the next thing I want to talk about is imagine Captain Levi is standing on a bathroom scale and he is in his elevator throughout this motion. What would the bathroom scale read? In terms of the reading, the dial, would he get a higher reading, the same reading as before, or would he get a lower reading for his weight, okay? Or reading on the scale, let's just put it that way. So, what do you think? Here's a good time to pause and just to quickly put your thoughts down on the page. Alright, and if you said he would feel the same, you would get the same reading when there's no change in his weight. That is true. That's probably the easiest one to fill out. And when he feels heavier, okay, when he feels heavier, he feels the ground is pushing up against him with more pressure. At the same time, he's going to be pushing down on the scale with a higher pressure as well, with force. So that would register a higher reading. So absolutely. And by process of elimination, he would get a lower reading when he feels lighter. Bathroom scale is not going to feel that from Levi as well. Okay, so here we got a kind of a physical basis to work off of. We can use this to further analyze our problem. So if the bathroom scale reading is changing, is it measuring his weight? or is it measuring something else? So let's go in this in a little bit deeper, okay? Now, first things first, in physics, weight is the force due to gravity acting on us. And we know that Fg is equal to mass times gravity. Levi is probably not going to lose any mass during that elevator. It's like he barfed or something. That's not going to happen. So this should not change. Mass should not change. That should stay equal. Acceleration due to gravity on Earth, we know, is 9.81 meters per second squared in the downwards direction. And in an elevator, if you're going up a few floors, the acceleration due to gravity is not going to change too much because the height comparison relative to the distance from the surface of the Earth to the center of the Earth is very small in comparison. So that's very insignificant. This acceleration due to gravity is not going to change a lot. So his weight, Levi's weight, is not going to change. Not very significantly, at least. So the bathroom scale is changing its reading, and Levi's weight, actual weight, is not changing. What is the bathroom scale measuring? So let's analyze this using a free body diagram. Let's put Captain Levi here on a scale, okay? And think about the forces acting on Captain Levi right now. We know there's the force due to gravity acting on him. That's his weight, and that's not changing. And there's another counterbalancing force, which is the normal force that is produced from him pushing down on the bathroom scale, and the bathroom scale pushing with an equal and opposite force on him, Newton's third law. So how does that attribute or contribute to him feeling heavier or lighter, or are they related? So let's think about it this way. If Captain Levi is feeling lighter on the scale is going to push back at him with a smaller force. Therefore, the force due to Fn, which is a contact force, must be also smaller. So the Fn, the normal force that he feels, has to do with the bathroom scale, and maybe that has something to do with him feeling heavier or lighter. To conclude, the bathroom scale measures the normal force acting on Captain Levi, which is changing throughout his trip. So maybe the reason why he's feeling heavier or lighter has to do with the normal force and not his actual weight. Oh, that is so weird. So then what you feel right now is not actually your weight. It's your normal force. And we have a special name for that, and that's called your apparent weight. And your apparent weight is not your actual weight, which is, we call it your force due to gravity, which we talked about before, okay? So these are two separate concepts. Fn, apparent weight, Fg, your actual weight. What you feel is your apparent weight, not your actual weight. Think about when you're in the elevator next time, and when the seat of the elevator is pushing against the bottom as you're going up and going down. So now you might be thinking, well, if I'm feeling heavier or lighter when I'm in an elevator or any kind of amusement park ride, if it has nothing to do with my actual weight, well, if it might have to do a little bit with it, but if the main reason isn't that, then why is it that we feel that way? Where does that come from? To do that, we have to go back to what we talked about earlier and discuss the times where you felt no change in weight, heavier and lighter in the elevator. So I'm going to write down just to quickly jot down all the times that these particular situations would happen in your elevator. When there is no change in weight, so when Levi's standing on the bathroom scale, he's feeling no change in his weight, that's when the elevator is at rest. Or it's moving at constant speed, so in middle of the elevator ride. And you might notice very well that in these situations, the acceleration of the elevator is actually 0. When the acceleration of the elevator is 0, we know that the net force acting on Levi at that time must also be 0. If we draw a free body diagram acting on Levi right now, we know that the two opposing forces must balance on an object for that person or that object to not be accelerating. In this case, Fn must be equal to Fg. Okay, that's not telling us much. Let's talk about the next one, where Levi in this elevator would feel heavier. That happens when the elevator is about to go up. I'm just using my signs there just to shorten it. Or when the time when he's coming down, but the elevator is slowing down. So in these cases, he's about to go up. That's the elevator speeding up, going up. Here we have the acceleration of the elevator in the upwards direction. When Levi is coming down in the elevator and slowing down, the elevator is decelerating, which means the acceleration must be in the opposite direction compared to down, which gives us the acceleration of the elevator in the upwards direction. Okay, so when Levi feels heavier, the acceleration of the elevator is in the upwards direction. Ooh, we're starting to see a pattern now. Okay, so F net equals to ma. The acceleration is upwards, which means the F net, the sum of the forces, must also be in the upwards direction. If we draw the free body diagram on Levi, with Fg being the same as before, in order for the forces to be unbalanced, for a net force in the upwards direction, his normal force must be larger. Hey, doesn't it match what would happen on our bathroom scale if you're standing on it? Interesting, hey? So your Fn is now greater than your Fg. So your bathroom scale would get a larger reading. This is when I can actually tell you, you're allowed to do this at home. You can put a bathroom scale in the elevator and go on it. That's fine. You can do that at home. The last but not least, when Levi is feeling lighter in the elevator, this we saw before, is when the elevator is going up and slowing down. I remember when I was younger and I lived in an apartment building, the elevator's about to reach the top floor, I would try to jump at the right moment so that I get a little bit more air. Yeah, fun, right? So there's that, where you feel a bit lighter. And the other time when you feel a little bit lighter is when the elevator's about to descend, when it starts to go down. So in both these cases, let's take a look. You're going up. You're about to stop while going up, so you're decelerating, okay? Decelerating, going up. Acceleration would be in the opposite direction, so acceleration is downwards, okay? In the other case, when the elevator is about to come down, so elevator's about to come up, it's speeding up, going down, acceleration is in the downwards direction. So in both these cases, acceleration is downwards, meaning F net must also be in the downwards direction. If we draw the free body diagram acting on Levi, Fg is the same, and an only way to give an F net going down is for Fg to be larger than Fn. Fn's going to be shorter, and hey, that's the time when your bathroom scale would read a smaller reading, and also when you would feel lighter. So here, your Fn is smaller than Fg. So notice, here we have a pattern. The pattern is when you feel heavier or lighter, has to do with your Fn, yes. And the reason why your Fn is changing is not because of your actual weight, has to do with the acceleration of the elevator. So that was different from before. You have an accelerating body causing you to feel heavier or lighter. Otherwise, why would amusement park rides be fun, right? If they didn't accelerate it. So this is the key thing I want you to grab. Your Fn changes depending on your elevator's acceleration. So to sum it all up, here are the key points. The first thing we talk about is, what is this force that attributes to you feeling heavier or lighter? That's not your Fg, it's your Fn. The name we have for it is your apparent weight. When your apparent weight changes, that has to do with your elevator accelerating up or down. And when the elevator is accelerating up and down, when it's heavier, when you feel heavier, your Fn is larger than your Fg, the acceleration of your elevator is upwards. When you feel lighter, it is the opposite. Fn is smaller than Fg, acceleration of the elevator must be downward. So hopefully that sums everything about elevator problems for you and a little bit of idea how you can tackle these problems. I thank you very much for watching Elevator Problems featuring Captain Levi on Attack on Titan. Fat Mama Physics signing out!